So the second video in our 3-video series on Michaelis Menten kinetics is going to be on competitive inhibition. So competitive inhibition. So reminding you again, if you haven't yet watched the first video, which is on sort of standard Michaelis Menten kinetics, make sure to do that so you have sort of a framework of how we think about how things operate normally, and then we'll see how things deviate once we have, in this case, a competitive inhibitor. All right, so again, to think about how things happen normally, we're going to think about enzyme binding substrate reversibly to form that enzyme substrate complex, and then do chemistry to generate our product. So this equilibrium between enzyme binding substrate and then forming that enzyme substrate complex and then free enzyme and substrate is our Km. And then our chemistry step is that irreversible process. And we're assuming that chemistry is irreversible to kind of make things be a little bit simpler. So this is what we're going to refer to as on pathway. So on pathway. So what happens when we think about inhibition is we have an inhibitor that can potentially bind to the enzyme. And so in this case, when we think about the inhibitor binding to the enzyme, again, it does so reversibly to generate an enzyme inhibitor complex. And the key is that there is no reaction that happens when the enzyme is bound to inhibitor. And so this pathway here is what we refer to as off pathway. So off pathway using red, again, to indicate that that is a non-productive pathway. So what happens here in this situation with competitive inhibition is that really we can think of there being like a choice for the enzyme. I cannot spell today. Choice for the enzyme. Okay? It's either going to bind substrate or inhibitor. And the fact that there is a choice here between the substrate or the inhibitor is why this is competitive inhibition. Substrate and inhibitor are competing for the same binding site. Okay? And that's also why, as an analogy, I want us to think about musical chairs. We're going to have 2 games here that we think about sort of as analogies or ways to think about the differences between competitive inhibition and then what we'll see in our next example, which is going to be uncompetitive inhibition. Competitive inhibition is the easiest one probably to think about sort of conceptually. And the musical chairs analogy, I think, resonates well with people because you can imagine there's 1 seat for potentially 2 people, or a number of seats for any variety of numbers of substrates or inhibitors. And what we have with this choice is this concept of thinking about a bifurcation of our pathway. Bifurcation of our pathway. And it's really another word, that's just a fancy word for a splitting. So we're splitting our pathway off. We have a productive on pathway option and then a non-productive off pathway option. The last thing to kind of highlight here is I do a lot of anthropomorphization, right? I kind of make it seem like there's human characteristics for our molecules, like they really have choices. At the end of the day, remember that choices really come down to probability. And in this case, if we were to do our musical chairs analogy, the one that we talked about in class, is imagine that we had boys and girls that were participating in musical chairs. And if we wanted to stack things in the favor so that girls would win, well, we play the game, say, having 100 girls and 1 boy. That's going to pretty much ensure that a girl is going to be the one that sits in that last chair. Right? That's just a probability situation. So the same is really true here, and that's going to play out when we consider sort of the different ways that we can manipulate whether we are more off pathway or more on pathway. Okay, so continuing with the discussion of this off pathway, we can apply just like we had a Km, that Michaelis constant that had to do with the equilibrium between free enzyme and substrate and the enzyme-substrate complex, we can think about a similar equilibrium constant, this Ki value. Again, thinking about that being a Kd value. What is the enzyme's affinity for the inhibitor? The Ki value is going to be an important parameter that we want to think about when we're understanding how competitive an inhibitor is, how powerful or potent an inhibitor is. So there's two things that we're going to consider when we consider what we call enzyme or inhibitor potency. And the first is just kind of identifying that there's going to be a certain amount of inhibitor that we're considering. And so if we want to have potent inhibition, we want to have a high concentration of inhibitor. Another way to sort of have potent inhibition is to have a small Ki value. Remember, small Kd values, or in this case a Ki value, represents a small concentration of inhibitor you need to have to effectively form your enzyme inhibitor complex, right? So small numbers mean a small concentration necessary to sort of have your half binding sort of situation, okay? So if we want to think about sort of inhibitor potency, so we want to think about how do we have potent inhibition. Okay, we are going to measure this potency by a factor that we're going to call alpha. So this is measured by this term called alpha. Okay, if we think about ranges that we have for alpha, alpha is going to go between 0 to infinity. And this will make sense when we actually look at the equation that we have here. I'm just going to move this up just a little bit. I've run sort of out of space here. All right, so when we think about the ranges that we have for this, so here's the equation that you want to think about for alpha, okay? So alpha is going to be equal to 1 plus the inhibitor concentration over the Ki value, okay? So again, the inhibitor concentration, this inhibitor concentration reflects how much inhibitor you have, and use some highlighting here just to kind of show where these pieces are, right? So how much you have, that's really represented over here. If we have a high concentration of inhibitor, we're going to be pretty potent. Again, looking at how this plays into this alpha sort of situation, so alpha here. If we want to maximize alpha, alpha is a potency factor. If we want to have a large alpha value, one way to do that is to have a high concentration of inhibitor. So that's going to be 1 plus high number in our numerator is going to add something significant. So it's going to move us towards the infinity side of this range. The other piece that we want to think about, okay, is this Ki piece. And Ki reflects how tightly the enzyme binds inhibitor. So this is how tightly you bind, okay? So picking, again, to highlight how tightly you bind, again, small Ki value is going to reflect binding tightly. So putting both of these together, let's say you had both of these situations, high concentration of inhibitor that binds very tightly, large number in our numerator, small number in our denominator, makes this be a fairly significant number that we are adding to 1. We are creating a potent inhibitor situation. And again, this is our musical chairs kind of inhibitor. This is a competitive inhibitor. So the enzyme has a choice with who it's going to bind to. And now this is going to become important when we sort of think about some of the hallmarks that we have of inhibition. So now we're going to map on how we think about this modifying our standard Michaelis-Menten equation. Okay, so remember, here's our standard Michaelis-Menten equation. V naught equals V max times substrate concentration over Km plus substrate concentration. Okay, so when we think about mapping on competitive inhibition, here's what happens. We get V max times substrate concentration over alpha times Km plus the substrate concentration. So this is where this potency factor sort of comes in. Okay, it's multiplied by Km. So what does this mean? This means that this alpha Km really becomes what we call Km apparent. It becomes apparently larger because it's scaled up by that alpha term. So this is the apparent Km, and it's scaled up by our alpha term. Okay, so the potency of our alpha term is going to dictate kind of how we do this. Now, one of the things to highlight, we're going to write this down, but I want you to see it mathematically here. When we start putting a number in our denominator that is 1 or greater, right? I shouldn't say 1, that is greater than 1. If we have some potent inhibition, this is going to mean that we are decreasing this entire value, which means we are decreasing V naught. That makes sense. We're doing inhibition. We should slow down our reaction. So let's map on what that actually looks like with the two sort of graphs that we are used to seeing. So the first graph that we're going to look at is a plot of V naught as a function of substrate concentration, right? And when we have no inhibition, let's say that our line looks like this. So this would be alpha equal to 1. That's no inhibitor. As we start inhibiting, we are going to make this reaction slower and slower until we have a more potent inhibitor. So inhibition, okay, is always going to decrease V naught. So inhibition, or let's say inhibitors, will always decrease V naught. They're always going to make it slower, right? And the more potent of an inhibitor they are, the larger that alpha value is, the larger the denominator, meaning the smaller the V naught. And that's all perfectly translated with these graphs that we said make intuitive sense, right? We can think about the reaction velocity as a function of substrate concentration. So remember, when we take this data that makes intuitive sense and then we plot it as a Lineweaver-Burke plot, that's where we can get useful information. So let's map on a few things that we're going to see here, okay? So if we want to think about sort of what our normal situation is, let's say we have this line. This is going to be alpha equal to 1. Now remember, this is going to be a little bit weird to think about because we're plotting this double reciprocal, 1 over V naught versus 1 over substrate concentration. So let's think about what happens then when we start inhibiting, okay? Now I'm specifically drawing this for what I know, I want to make this be a straight line here. What I know is going to be the case for a competitive inhibitor. So this is, go back to writing here, alpha equals 2. And then let's go to our alpha equals 4. And I'm very intentionally drawing these this way because I know that the hallmarks for a competitive inhibitor is that we do not affect Vmax. So right here we can see that all of these points kind of intersect in the same region. And remember, the y-intercept of a Lineweaver-Burke plot correlates to 1 over Vmax. So Vmax is unchanged, okay? Remember, the other piece that we get from our Lineweaver-Burke plots is information from the slope. So the slope in this case is going to be equal to alpha times Km over Vmax. Remembering that that scaling factor gets put with the Km term. All right, so what does all of this mean, and what are the 3 things that I want to make sure that you know and remember are hallmarks of competitive inhibition? So hallmarks of competitive inhibition. Okay, the first is that we are going to increase our Km. We are going to scale our Km value by our alpha term, right? Our alpha term, the potency that we have there, okay? The second hallmark is that there is no effect on Vmax, right? We can see that graphically, knowing that all of these converge on the same y-intercept, the same Vmax value. Now, we may not necessarily see it from here, but what that means is all three of these lines will eventually converge on the same Vmax value. Remember that Vmax value represents the maximum velocity that I'm going to be able to get. So they're eventually going to converge on that point, but early on, they are distinct from one another. And so how do we get to that kind of Vmax? Okay, that's the third hallmark that we have here, is that inhibition can be overcome by just increasing our substrate concentration. So inhibition can be overcome by increasing our substrate concentration. So sort of coming back to that probability piece and thinking about our situation here with our boys and our girls having a game of musical chairs, right? So let's say that our inhibitor was really sticky. Let's say that we had a girl here that had a really sticky pair of pants that we're gonna like find the seat and sit down, right? High potency factor, if you will. If we want to make sure that she doesn't sit in that seat, we would have to have a huge sea of boys so that from a probability and statistics standpoint, she is not likely to find that seat and a boy would be able to kind of come in there. So we can sort of outcompete the inhibitor by having high concentrations of our substrate. So those are the three hallmarks that we're going to have of competitive inhibition. So the last little piece I want to talk about here, and I'm going to copy this graph here just so that I can have it on the next slide to talk about our last little piece here, is to talk about how we actually would use this data when we're in the lab to obtain some important kinetics parameters. So one of the things to think about is that when we take the ratio of the slopes, important to highlight that Km and Vmax are inherent properties of an enzyme. Even in the presence of inhibitor, right, we're going to have a Km and a Vmax for a competitive inhibitor that really are the same. What happens when we start putting an inhibitor in is the Km value appears to be larger, and that's because it's being scaled by that alpha factor, but Vmax remains unchanged. So what we can do is we can take the ratio of the slopes for our different experiments, and that's going to give us our alpha, okay? So again, taking this slope, right, and dividing by this slope, that should give us that the alpha for that blue line is 2. Taking the ratio of the red line to the black line slope, that should tell us that the potency of the inhibitor at that red line's concentration is going to be 4. So again, those alpha terms, we know the concentration of the inhibitor that we used to get this red line and this blue line, right? So if we wanted to figure out sort of what the money parameter is, remember that alpha is going to be equal to 1 plus the inhibitor concentration over the Ki value, okay? This alpha term is something we can get from the ratio of the slope, so now that becomes a known variable in this equation, okay? We can take this alpha term, plug it in over here, and then because we know the concentration of inhibitor that we use to kind of do that experiment, this is going to be a known value. So that's going to be known, okay? And then the piece of information that we're really interested in is this Ki value. And why this is really important, this is sort of the money value, right? This piece of information is really the money amount for drugs, right? You want to have a drug that binds very tightly. Again, having that small Ki value, and that's important because that ultimately translates into a small dose. Small doses for drugs are important because not only does that mean you don't have a lot that you have to take, there's fewer side effects, and importantly, it's going to likely cost less to make if the patient only needs to take small amounts of it. All right, so that's our thought process that we have with competitive inhibition.